For this video, I want to talk about valence shell electron pair repulsion theory. VSEPR is something that you've heard about in Chem 110 and or Chem 190 here at HWS, and usually we talk about valence shell electron pair repulsion theory in the context of the hybridization of a molecule and or which atomic orbitals each atom is using to build up the molecule as a whole. The reason why we care about this is because ultimately the shape of the molecule is determined by trying to spread things out as far apart from each other in space as is possible, and the hybridization is how the molecule does that. But if we know what the hybridization of an atom is, we can predict its shape. If we know the shape of the molecule, we can predict its hybridization. So the concepts play back and forth. In order to talk about this well, let's define the Cartesian coordinates that we will be using. This is standard right-handed three-dimensional Cartesian coordinates. So z-axis is going to be up and down, x-axis is coming towards you and going back into the wall, and the y-axis is in the plane of the board. So once we've defined those axes, then we can talk about the orbitals we're going to use in the molecules in question. For any hydrogen atom, the 1s orbital is the orbital that's going to, but as soon as you start talking about heavy atoms like carbons and oxygens and so on, then the 1s orbital is an inner shell pair of electrons, and it's not involved in the bonding. It's not involved in making bonds with other atoms. It's simply inside the carbon itself. So the carbon is going to use its 2s orbital, which looks like a sphere, and three 2p orbitals, each of which is vaguely dumbbell shaped. I have drawn the way these are usually represented in textbooks. The actual reality of the orbitals doesn't look like that, but this is the way you're going to see them drawn. And there are three different p orbitals, each aligned with the axes we've defined. So the pz orbital is going to be vertical. The x orbital, the px orbital, comes out towards you and back into the board, and then the py orbital exists in the plane of the board. Any carbon atom will use these orbitals, but any other member of the second row of the periodic table, like an oxygen, like a nitrogen, would also use the same orbitals to make bonds with. So anyhow, we have the Cartesian coordinate system, we have the orbitals. Now, which molecule will we be using? I've drawn out a Lewis structure, and I've also drawn out a line-angle structure to match. This is the way I prefer to draw molecules, in line-angle form, but the nice thing about the Lewis structure, the Lewis dot structure, is that it is explicit about the location of every lone pair and every atom. And so because it shows you exactly where things are, this is useful as we talk about VSEPR and bonding and so on. So the first rule of valence shell electron pair repulsion theory is that you're trying to spread things out as far apart as possible in space. So what you really are interested in knowing is how many different bonding areas or lone pairs are present around every atom. So this carbon has 4 different bonding areas, 4 pairs of electrons that is trying to spread apart as far as it can. This carbon has 3 different bonding areas, an oxygen and these 2 carbons. This carbon has 4 different bonding areas, 2 hydrogens, 2 carbons. This carbon has 2 bonding areas, a carbon on either side. This carbon has 2 bonding areas. This oxygen has 3 areas, 1 for bonds and 2 for lone pairs. So broadly speaking, each one of these atoms is trying to solve the problem of how to spread the electrons as far apart from each other as they can get. And the reason why they're doing that is because every single pair of electrons, whether it's non-bonding or bonding, is a minus charge. It's an area of minus charge, and minuses are going to repel each other. So these lone pairs are repelling each other, and they're also repelling this bonding area as well. And so what happens is you try to spread out as far as you can. If you have 2 bonding areas, like for this carbon, then the best you can do is to spread those 2 bonding areas 180 degrees apart, and the molecule will be linear. As soon as you have 3 things, the best you can do is a 2-dimensional flat surface where you have 120 degree bond angles separating things. But as soon as you have 4 things that you need to push as far apart as you can, then you use 3-dimensional space and the angles become 1095. So said another way, and you have encountered this before, the bond angles that we expect for anything with 4 things bound is 109.5 degrees. The bond angles for a standard sp2 hybridized atom, which is to say you've got 3 things that you're trying to push as far apart as possible, is 120 degrees. This carbon again has 4 areas it's trying to spread apart. That makes it 1095. And then this carbon is going to be linear. This carbon also is going to be linear. This oxygen is going to be linear, but the separation between the lone pairs is going to be on the order of 120 degrees. And the separation between a lone pair and the double bond is going to be about 120 degrees. The idea is simple. If you have 2 pairs of electrons that are going to repel each other, you push them as far apart as possible, 180 degrees. If you have 3 pairs of electrons you need to separate, 120 degrees is the best you can do. And with 4 things, it's 1095. It's just geometry. All you're trying to do is push these things as far apart as possible. The standard demo for this is to tie together balloons, and you'll just see that balloons will automatically assume the shapes that we are telling you to do. For pure geometrical considerations, we know that these are the bond angles that each individual element will assume. So how do the actual atoms in question, the carbons and the oxygen, create these bond angles? Well, the answer to that is by hybridizing atomic orbitals together. So this carbon, because it has 4 things attached, it needs 4 orbitals to put those electrons into. And what it will do is mix together each of these 4 orbitals in turn into 4 different sp3 hybrids. So you have 4 sp3 hybrid orbitals in order to spread around the electrons as far apart as you can. Obviously, this carbon, also trying to be separating 4 things as well as it can, will also have 4 sp3 orbitals as the places in which it places those electrons. These 2 carbons are different. They only need to use 2 orbitals to set up the sigma framework, the single bond framework. So it only really needs to combine s orbitals and orbitals that are in the plane of the board. In other words, they will be using their py orbital, each of them, in order to go ahead and make these bonds. So in order to make the linear bonds, each of these carbons will use 2 sp orbitals, one pointed that way, one pointed that way, and we'll have 2 leftover p orbitals. Said another way, if this carbon atom is using the py to make its 2 sp hybrids, what are left over are the pz and the px orbitals. One orbital coming out this way and one orbital in this direction. This carbon has to use the same orbitals to match, so 2p and 2 sp orbitals. So there's 2 different p orbitals, pz and px presumably, and it also mixes together the s and the py to create 2 sp hybridized orbitals. This carbon must also be using the py orbital to spread the electron density out in the direction of the board. Said another way, this carbon is going to have 3 different sp2 hybrids that it makes, one that's predominantly in the z direction, and 2 that are predominantly in the y direction, but with a little bit of negative z component. What's left over from this carbon is an empty p orbital, and that p orbital is going to be making the bond with the oxygen. So by the same token, since the oxygen is using that p orbital to make a double bond, the oxygen has a p orbital for the double bond and also is using 3 different sp2 hybrids to spread apart its electron density as far apart as possible. Again, the oxygen is going to be using predominantly a pz orbital, mostly in the negative direction, to make its sigma bond. And then there's going to be mainly py components over here with a little bit of positive z mixed in. So the main problem that each of these atoms is trying to solve is that the s orbital is a relatively low energy orbital, but it's symmetrical, it's not directional. Each of the p orbitals are directional, they're higher in energy than the s, but they also point in nice directions. The problem is that the angles between any 2 p orbitals are 90 degrees, and we can do better than 90 degrees if we mix these together in a smart way, or if we at least allow them to be mixed in ways that might lower the energy of the overall system. Since I'm talking about energy, I need to draw an energy diagram. So if you're one of our heavy atoms, the carbon or the oxygen, you have a 2s orbital and you have 3 2p orbitals. Before we make any bonds, these p orbitals are all the same, they're all the same energy, and this s orbital is lower in energy. But rather than using these 4 orbitals like this, what the atom would like to do is mix them together. So if you're, say, this carbon, you can improve your bonding overall by mixing all of the orbitals together to create 4 orbitals that end up lower in energy than the original p orbitals, but higher in energy than the original s. But the real advantage is that these p orbitals are only 90 degrees apart in terms of bond angles, whereas the 4 different sp3 hybrids that you generate are 109.5 degrees. Said another way, if you take this s orbital and mix it with this pz, you get a directional orbital. You get 2 directional orbitals, in fact. But once you mix in the other 2, then you end up with 4 directional orbitals, each of which points in a slightly different direction. Imagine I'm the oxygen atom instead of the carbon, and I only need to make bonds to 3 different things. Then it doesn't make sense for me to make 4 different sp3 hybridized orbitals, when in fact I could do better if I mix in more of the s relative to the p's and I lower the energy of the hybrids that I generate. So now I'm going to generate 3 sp2 hybrids that are going to be lower in energy than the sp3 hybrids would be. Part of the reason why I care about this is because I only need to use the z direction p orbital and the y direction p orbital, and I don't need any of this component to spread things out as far as I can. So the px orbital can be left over. Specifically, when this is done, the 3 sp2 hybrids are what oxygen is using, and what's left over at the original energy is the px orbital. The idea is that the oxygen would rather mix in its s, the pz, to create 2 directional orbitals, one which mainly points down and one which mainly points up, and then to separate that one into a component that points up and right, as well as a component that points up and left. So I'm going to go ahead and draw out the process by which this oxygen will create its hybridized orbital to better illustrate the process. So what the oxygen does first is mix together a s orbital and a pz orbital. All of this fundamentally is about math. So if you are interested purely as an organic chemist, I draw these crazy little pictures. If you are more interested in physical chemistry, when you take quantum chemistry, you will understand a bit more of the math that's underlying all of this. For the purposes of the pictures, what you need to know is you can mix together orbitals as long as you always do them in linear combinations of orbitals, which means essentially you can mix together both in a positive direction if and only if you then subtract one from the other. So a pz orbital can be mixed together with a 2s orbital, or a pz orbital can have the 2s orbitals subtracted from it. But what's really going on here is that actually what I want to do is consider that to be a minus 2s orbital, or really what I want to say is that the 2pz orbital adds to it a 2s orbital with the opposite phase of the 2s orbital that I used originally. I don't want to get into the details of the functions, but what matters in quantum mechanics to some extent is this function known as psi squared, which essentially amounts to the probability of finding an electron in a given spot. If you have a pz orbital, there are 2 lobes with high probability of finding the electron, and a node that has 0 probability of finding the electron. So the electron that would occupy this pz orbital can either be in one lobe or the other, but it will never show up in the middle. And that's what I'm attempting to draw here. So psi squared is a measure of the probability of finding the electron. And what that is the square of the wave function. The wave function is a function that actually has both a positive and a negative component to it. It has phases. And so this function, when squared, tells us the probability. So the moral of the story is that when we are adding these 2 orbitals together, what we're doing is adding 2 different waves together, essentially 2 different sine waves. And so areas where you have the same phase will tend to add, and areas where you have opposite phases will tend to cancel. Said another way, I can mix together the 2pz orbital and the 2s orbital and create a new orbital, one where these 2 areas add together, but the out of phase areas cancel. And when I mix together the pz and the other phase of the 2s orbital, the blue will be dominant and the other side will cancel. Let me show you what that looks like. Once I have added the 2 waves together, what I create is a new orbital where there's a much larger lobe where the 2 in-phase components added together, and a smaller lobe where the out-of-phase components added. By the same token, I have an equal and opposite orbital that was created at the same time, where the blue portions add together and the colorless and blue portions cancel slightly. So when I mix together a pz orbital and a 2s orbital, I get 2 sp hybrids that point in the z direction, and they will point equal and opposite to each other. One will point generally down, one will point generally up. So if the oxygen is going to use these orbitals to make a bond to the carbon. Specifically in the sigma bonding case, the oxygen will use this orbital to make the bond with the carbon because the lobe points down. Meanwhile, this leftover p orbital pointing in the up direction will now be split by mixing in some of the py component to create two new orbitals, one that points up and right for the lone pair, and then up and left for the other lone pair. So what's going to happen now is the oxygen is going to mix together the 2spz orbital it has already generated that points in the up direction with the 2py precisely in the phase that it was originally, and also with the 2py where I have flipped the phase so it's pointing the other direction. This will create a new linear combination of orbitals. So the idea now is that if you take together this 2spz orbital that points mainly in the up direction, we mix in the 2py with the lobes that tend to add together in the up and right direction, you should get a 2spypz orbital that points up and right. And by the same token, when you mix together these orbitals, you get one that points up and left in the area where the lobes largely mix together. Now, bear in mind that I'm probably doing some violence to the actual math, and that we need to factor in how that orbital plays a role. But this is a decent qualitative understanding of what's going on. This oxygen needs to have three different sp2 orbitals, one to make a bond with the carbon, and two to point in different directions to create space for the lone pairs. Okay, so how does everything change if you're a carbon? Well, if you're the carbon, you clearly need to mix in the last remaining orbital, the px orbital, in order to get stuff that points in the forward and backwards direction. Now, I haven't illustrated that, but the 109.5 degrees, in order for that to be true, what must be true is that one of these hydrogens must come out of the board toward us, and one of the hydrogens must also go back away from us into the board. That's the only way, this three-dimensional depiction, this is the only way to get a tetrahedron. It's the only way to get 109.5 degree bond angle. One of the hydrogens comes toward us, one of the hydrogens goes back in. And in order to do that, we need to use the px orbital as well, the only one that comes out and the only one that goes back into the board. By the same token, these two hydrogens then, one must come toward us and one must go back away from us. Again, it's the only way to spread things out in space as best you can, to use all three dimensions available. Everything else is going to be in the plane of the board, but the hydrogens, one comes out toward us, one goes back away. And the way you create orbitals that do that is you take hybrids like the ones we've already generated and then mix in the only orbital that comes out toward us and goes back in. So the moral of the story is that if you need to separate two things in space, what you do is you mix together an S and whichever P you need. If you want it to be spread apart in the Y direction, you mix together an S and a PY, and that will do it. If you want to spread things apart in the Z direction, you mix together an S and a PZ, and that will do it. If you mix together an S and a py, then the other two orbitals aren't being used. So this carbon has two p orbitals that aren't being used. One that comes out toward us, the px if you will, and one that's largely vertical, which is the pz component. So it's using mostly the py to make that bond. This carbon as well. This carbon, however, is using both the z direction and the y directions to make its single bond, its sigma bond framework. So what's left over is going to be only the px component. These carbons need to use all three p orbitals in order to spread four things apart as far as they can, so they need to make sp3 hybridized orbitals. In a nutshell, what we're talking about is spreading everything apart as far as we can, and the reason why we call these atomic orbitals is because this carbon is mixing together four orbitals that exist on that carbon atom in order to create four new orbitals that then are combined with other orbitals to make the actual bond. This carbon creates the four orbitals, and notice that it points one of those orbitals towards this carbon. But this carbon then will actually be pointing an orbital back toward it, and that combination of orbitals becomes the molecular orbitals. So what I want you to take away from valence shell electron pair repulsion theory, more than anything else, is that you need to understand what these bond angles are, and that will inform what the underlying hybridization is. That will tell you where the orbitals are. So you need to know bond angles, which is to say, you need to know what this thing will actually look like in space. You need to understand that those bond angles imply a certain hybridization. Or maybe you'd rather think of it the other way. If you have a certain number of things to bind, that implies a certain hybridization, which then creates the angles that you're going to see. If you only need to bind two things, well, you can put them 180 degrees apart, which means you need to use an sp orbital to do that, one in each direction, and you have two p orbitals left over. Or alternatively, you can think, hey, I have four things I need to bind, therefore I'll make four sp3 hybridized orbitals, and they will happen to point 109.5 degrees apart from each other. But now it's time to pivot to molecular orbitals instead.